conventional topological, say from band bending at the surface. So one suggestion against this third is that we see these surface oscillations on many different crystallographic orientations and many different samples. Reasonably well to some exponential with some characteristic length scale of, say, 600 nanometers. So theoretically, we expect that any kind of quantum oscillation phenomena is suppressed by some Dingle factor, which is basically inversely proportional to the cyclotron frequency times the scattering time. And so here, the effective cyclotron frequency times scattering time is basically the time it takes to complete the orbit and the scattering time for each segment. So there's two pieces. The first is this bulk part, and the second is this bulk part, which depends on the thickness, and the surface part where you're sliding along the arc. And importantly here, there's some subtlety of what's the correct scattering time to phase the quantum oscillations. And on the surface, and in conventional oscillations, it's actually just the full scattering rate. Every scattering process is dephases you. And the bulk is a bit more subtle because you're kind of riding on this chiral lambda level. And this chiral lambda level doesn't turn around for anything. So it can just ride straight through disorder. So the time it takes to go through the bulk, if I'm sticking on this chiral lambda level, is independent of what the impurity potential. So the only thing that can scatter me in the bulk is if I can turn around to some non-chiral state. And that, in the regime where I'm seeing bulk quantum oscillations, requires some sizable momentum transfer. So this bulk scattering time we expect to be more like a transport scattering time, which these materials is much longer. And in fact, we can extract the transport lifetime by looking at some finite size effects in the magnetic field. So if we apply the magnetic field not perpendicular to the surface, but along the parallel to the surface,